स्टार्ट करते हैं. What is enthalpy of a reaction? As I told you yesterday, that what is the change in the reaction? Is the heat absorbed or released? That is basically the enthalpy of the reaction. If the reaction is exothermic, which means heat will release from the system. That shows the reactants having high heat content. The reactants having high enthalpy. That's why when the product is formed, energy is released, heat is released, and the products having less enthalpy as compared to reactants. If we talk about endothermic reaction having products having more enthalpy as compared to reactants. That's why we are adding energy in endothermic reaction, because reactant having very less enthalpy, very less heat, they are not able to make a product by their own. So we need to provide that system, that reaction energy to increase its enthalpy. So when we are providing heat to that type of reactions, then products having a high enthalpy. Endothermic reaction, the enthalpy change is represented as a positive sign, and in exothermic reaction, enthalpy change is represented as a negative sign, because in endothermic reaction, heat is given to the system, and in exothermic reaction, the heat is released from the system. So if the heat is released from the system, which means H2 is smaller and H1 is higher. So if you minus the smaller value from the bigger value, the answer will be in a minus. That's why exothermic reaction having a negative sign. On the other side, endothermic reaction having a positive sign, because when you are adding the heat, which shows H2 having a higher value of enthalpy and H1 is lower value. So when you are minusing the lower value from the higher one, then the answer will be in a positive. That's why endothermic reaction having a positive sign and exothermic reactions having a negative sign. According to the definition of the enthalpy of the reaction, here you can see the standard enthalpy of the reaction is the enthalpy change which occurs when a certain amount of the moles of the reactants as indicated by the balanced chemical equation. You must remember that there must be a balanced chemical equation. React together completely to give the product under standard conditions. So when you are going to check about the enthalpy of the reaction, you must keep the conditions standard. What are the standard conditions? Temperature must be 25 degrees Celsius and at the pressure must be 1 atm. On this temperature and pressure, you have to check out the reaction is endothermic or exothermic. There are two ways to check the enthalpy of the system: glass calorimeter and bomb calorimeter. We are going to discuss this later. Next, we having an enthalpy of formation. It sounds like that something is formed during a reaction. So compound is formed by its elements. The enthalpy change during the formation of the compound by its element is called enthalpy of a formation. You represent enthalpy of formation as delta H F naught. Delta HF naught. Enthalpy of the reaction, that was simple. You have to represent that as delta H. But when you are representing enthalpy of formation, so you have to write delta HF naught. Enthalpy of formation is the formation of the compound from its elements. In the formation of the compound, there must be the loss of some heat or the absorption of the some heat. So here you can see in this reaction, always condition must be standard. Temperature must be 25 degrees Celsius and pressure must be 1 atm. When magnesium oxide is formed from its elements, here you can see its elements magnesium and oxygen. When the compound is formed from its element is called the enthalpy of the formation. Otherwise, you are not going to say the enthalpy of the formation. If there are the molecules or the compounds who are making the new compound, then that is enthalpy of reaction. But when we are talking about the enthalpy of formation, which means formation of compound by its elements. So magnesium is an element, oxygen is also here an element because we are using half, which means not two atoms of oxygen, because we cannot use oxygen as a single atom, we always use it as a molecule. So that's why here written half, which means to cancel out with the two, there is just one atom of oxygen for one magnesium. Clear? So when the compound is formed from its elements, then the enthalpy is called as enthalpy of formation. It could be exothermic reaction, it could be endothermic reaction. Formation of magnesium oxide is exothermic reaction, so heat of formation of magnesium oxide is represented as a minus sign, minus 692 kilojoules per moles, which proves that the formation of compound by its elements could be exothermic or endothermic. And other example is of endothermic, also exothermic reaction in your book, not written about the endothermic reaction in your book. Well, endothermic reaction, some of the endothermic reactions are also represented as a enthalpy of formation. So next example is formation of carbon dioxide. Here you can see carbon dioxide is also formed from its elements, carbon and oxygen. So when the compound is formed from its element, then this is called as heat of enthalpy of formation. This is also an exothermic reaction. Next we having enthalpy of atomization. Atomization sounds like that atom is formed. So when you are making atom of an element, the amount of heat absorbed, this is called as enthalpy of the atomization. Enthalpy of the atomization. Here you notice only absorb is written, not evolve. Not evolve, which means atomization is only a endothermic reaction. Atomization, enthalpy of atomization is only an endothermic reaction. It could not be exothermic reaction. You must have to provide the heat to the system to make an atom. Without providing heat, atom will not form. Atom always form when there is endothermic reaction. So when 1 mole of gaseous atom, this is formed from its element under standard condition. As you know, standard conditions are 25 degrees Celsius and 1 atm pressure. So this is called as enthalpy of atomization. You are making atom, 1 mole of gaseous atom from its element. You are making an atom. So to make an atom, some amount of energy, some amount of heat content you need to provide to the system to take place this reaction. Always you need to provide the heat. There will no any type of a reaction in which heat evolve and atom form. Clear? So atomization having a endothermic reaction. Next we having enthalpy of neutralization. What is enthalpy of neutralization? It sounds like the reaction is of neutralization and heat content is, and the change in heat content we are going to observe. This reaction is always exothermic. When the neutralization reaction takes place, always heat evolve, always heat release from the system. That's why enthalpy of neutralization is in a negative, because always heat evolves from the system. So the standard enthalpy of neutralization is the amount of heat evolves when 1 mole of hydrogen. As we know, the neutralization reaction is the reaction of acid and base. Acid plus base react together, salt and water is formed. Salt plus water form. So acid provides H positive ion and base provides OH negative ion in a system. So according to the definition, when 1 mole of H positive ions of an acid reacts with 1 mole of an hydroxide ions of a base to make a 1 mole of water. The amount of heat that is evolved from the system is called as enthalpy of the neutralization. You must consider this, the representation of all these enthalpies are different, little bit different. Here you can see the enthalpy of atomization is represented as delta H A T then naught. And enthalpy of neutralization is represented as delta H N naught. So while you are writing in exam, so you must remember the representation of these enthalpies. Okay, so when 1 mole of H positive ion and 1 mole of OH negative ion from the base react together and making a 1 mole of a water, some amount of energy will release. So that energy that is evolved from the system, that enthalpy, that amount of heat evolved from the system is considered as the enthalpy of the neutralization. So the neutralization of sodium hydroxide, this is sodium hydroxide plus HCl, that is hydrochloric acid. NaOH is a strong base, HCl is a strong acid. So when they react together, they make 1 mole of water and evolve minus 57.4 kilojoules per mole of heat. Here you can see. So this is called as enthalpy of neutralization. Reaction of neutralization takes place and the energy that is evolved, the heat that is evolved is the enthalpy of that reaction. HCl is providing H positive ion, NaOH is providing OH negative ion to the system. That H positive ion and OH negative ion of these two compounds combine together, 1 mole of these two combine together and give you 1 mole of water. The remaining ions are Na from the sodium hydroxide and Cl from the HCl. They remains moving freely in a system in the form of ions. Next we having enthalpy of combustion. So combustion means the burning of something in the presence of oxygen. So in this reaction, always heat evolves. As we know, combustion is a reaction in that is exothermic reaction. In the same way, the neutralization is also an exothermic reaction in which also heat will evolve from the system. So when you are burning 1 mole of substance, all the definitions are similar to each other. Just you have to change 1 to 2 words and it will be similar to each other. While you are talking about neutralization, so talk about acid and a base. While you are talking about the combustion, so talk about the substance that, for example, the carbohydrates, they are burning in the presence of oxygen under standard conditions. So all the definitions, all the statements are similar to each other, but according to their heading, you have to change the terms. If you are making atoms, so talk about the atoms. If you are doing neutralization, so talk about the acid and a base. If you are talking about the formation, so talk about compound from its elements. So it is very easy to learn this topic because all the statements are almost similar. Just you have to change the main compound substances according to the heading. So what is enthalpy of a combustion? 1 mole of substance is completely burned in excess of oxygen under standard condition. The standard conditions are 25 degrees Celsius temperature and 1 atm pressure. So here you can see ethanol is burning in the presence of excess of oxygen. Carbon dioxide plus water is formed. The reaction is exothermic. This is a combustion reaction. As we know, in a combustion reaction, carbon dioxide and water is formed. If you are burning anything in the presence of oxygen, it will provide you carbon dioxide. You are doing combustion reaction. The products of combustion reaction, as we know, the sole products of combustion reaction are carbon dioxide and water, as we discussed this in our previous chapters. Sole products are carbon dioxide and water. So when you are doing the combustion reaction, you are cleared with this. The product will be carbon dioxide and water. Moles could be changed. It could be changed 2 to 3. It could be changed according to the substance which we are using to burn. This reaction is always exothermic. Always heat will evolve. Enthalpy of combustion is represented as delta HC naught. Next and the last one is enthalpy of solution. Enthalpy of solution is represented as delta H SOL. SOL for solution, then naught. So this is the representation of enthalpy of solution. The standard enthalpy of a solution is the amount of heat absorbed away. Now this reaction this reaction could be exothermic or endothermic. While you are making solution, heat could be absorbed, heat could be evolved. Both condition can happen. So this is exo or endo both. Enthalpy of a solution is exothermic reaction or endothermic reaction, depend upon which substance we are adding in a solvent, in a water, while making a product. Because when you are making the solution of ammonium chloride, this is an endothermic reaction, and when you are making a solution of sodium carbonate, that reaction is exothermic reaction. Before that, see this. The amount of heat absorbed or evolved when 1 mole of substance is dissolved in so much solvent. So means you have to take the 1 mole of a substance and take a large amount of solvent. Such amount of solvent that your substance is not detectable from that solution. So you have to take the excess of the solvent and 1 mole of your substance. That further dilution results in no detectable heat change, that there is a no detectable your product, your substance, you cannot observe the heat change. You have to make such a solution to check the enthalpy. Next is the examples of an enthalpy of solution. As I told you that ammonium chloride, when you are making the solution of ammonium chloride, that is endothermic reaction, which means when you are dissolving ammonium chloride in a solvent, you observe that the system is cool. Your container, your system will be cooled down. When you are dissolving sodium carbonate, then heat will evolve. And your container in which you are mixing your solution system will be heat up, because minus 25 kilojoule per moles of energy is evolved from that system. Next, the very most important topic we are going to discuss is the measurement of enthalpy of the reaction. How you can measure the enthalpy of the reaction? We are discussing that some amount of heat is evolved, some amount of heat is absorbed in a system while we are doing reaction, while we are doing work, while system is doing a work. So how we can calculate that enthalpy of the reaction? You can calculate the enthalpy of a reaction by 2 methods: glass calorimeter and bomb calorimeter. One by one we are going to see this, what is glass calorimeter and what is bomb calorimeter. First, see what is glass calorimeter. Glass calorimeter, here you can see the glass calorimeter. This one. This is the apparatus which is showing the glass calorimeter. Calorimeter is basically the apparatus in which heat is not evolved or absorbed in a system from the surrounding. We are isolated the system from the surrounding by using a good insulator. We are making the container in which we are doing the reaction, that is a good insulator. From that insulator, the heat is not going outside of the system and not coming inside of the system. So glass calorimeter is basically made up of glass. It is insulated from atmosphere by cotton wool. This glass calorimeter having 2 containers. First one is this one, and this one is the inner one. Between these 2 containers, the middle portion is fitted with the cotton wool to isolate this system, to insulate this system, because this cotton wool will help the system that heat is not quickly move towards the surrounding, or the heat from the surrounding not quickly come inside the system before we are going to calculate or measure the temperature of the reaction. This is a container in which we are going to do the reaction, and here you can see the thermometer. By this thermometer we are going to check the temperature, initial temperature before reaction and after reaction. So we are going to calculate two temperatures: initial temperature before the reaction and the final temperature. By this we can calculate the enthalpy change, that what enthalpy change takes place during the reaction. This is a stirrer. While we are doing the reaction, we have to continuously stir this. So for example, we are doing the reaction of neutralization. Mostly in a glass calorimeter, we check the enthalpy of neutralization and enthalpy of solution. So for example, we are going to do the neutralization reaction in this glass calorimeter. So what we need a base and a acid. So we are taking, for example, strong base NaOH and strong acid HCl. We have added hydrochloric acid. We notice the temperature from the thermometer. Initial temperature we checked out. After that we are going to add sodium hydroxide in it. When we will add sodium hydroxide, reaction will start. Neutralization reaction will start, because neutralization reaction is a reaction in which heat evolve. Heat is go out. So we no need to provide heat to the system. Clear? Because this is a exothermic reaction. So both the compounds, hydrochloric acid and sodium hydroxide, are present in the system, and we are stirring the reaction, and after time to time we are checking the temperature. When the reaction is ended, there is no increase in the temperature. So after, for example, 30 minutes, or we can select any temperature. After that we are checking the temperature on the anytime we are going to check the temperature. After 30 minutes, after 20 minutes, after 10 minutes is up to us. So we will get T2, the final temperature. At that point where no temperature will increase, which means that is the final temperature, that is the final enthalpy which is released from the reaction. That is the final amount of heat that is released from the system. So we are going to use the formula to calculate that heat which is evolved from the system. The formula is the mass multiplied by specific heat capacity multiplied with the delta T. Mass M representation, S is for specific heat capacity and delta T is for temperature change, initial and the final time. What is specific heat capacity? Specific heat capacity is basically the heat, the amount of heat which is absorbed or evolved to increase 1 Kelvin temperature, not degree, 1 Kelvin temperature of 1 kilogram of substance. Specific heat capacity is the amount of heat that is absorbed or released to increase the temperature of 1 kilogram of your substance. For example, your substance is water. So if the increase in 1 Kelvin of the temperature in a water, that amount of heat is called as the specific heat capacity of the water. Clear? Water, oil, metal having different heat capacities, different substances, different things having different heat capacities. We use, you know that in our cars we use water as a coolant. Why we use water as a coolant, not oil and any other substance? Because water having a very high heat capacity, very high heat capacity value, which means you need a higher energy to increase 1 Kelvin temperature of the water. That's why water having a high heat capacity. Mostly water is used as a coolant because water having a high heat capacity, you need a high amount of energy to increase the 1 Kelvin temperature of the water. Oil and other substances having a very less amount of specific heat capacity. For example, water having 14182 joule per kg per Kelvin. And if we are talking about the oil having 1670 joule per kg per Kelvin. So this amount is very less as compared to the specific heat capacity of a water. Specific heat capacity of a water is very high. So which means if you want to increase 1 Kelvin temperature of water, you need this amount of energy. And if you want to increase the 1 Kelvin temperature of oil, so you just need 1617 joule per kg per Kelvin energy. So which shows that water needs a very high energy. So that's why water is used as a coolant in a cars. So by the specific heat capacity of the substance, mass of the substance, and change in delta T, you can calculate the heat of the system. This is all about the gas calorimeter. Next we having an example number 2 and example number 2 and example number 3 we will discuss tomorrow. Now I'm going to discuss with you the bomb calorimeter. We have to finish this, how we can calculate how we can measure the enthalpy of the reaction. We will do examples inshallah tomorrow. So next we having a bomb calorimeter. Here, what is bomb calorimeter? This is also an apparatus which is created to calculate the enthalpy of the reaction. Here you can see bomb calorimeter. In a bomb calorimeter, we basically calculate the enthalpy of the reactions of combustion. Combustion is O. Combustion of food, fuel, or the other substance. So in a bomb calorimeter, we calculate the enthalpy change of the combustion reaction. Combustion of any of the food, combustion of any of the fuel, that how much heat is evolved from the food or absorbed. Mostly as we know in a combustion, heat is always evolved, not absorbed. So this is exothermic reaction. Heat will evolve. We will check that heat from the thermometer. Here you can see. So we are taking the steel cylinder that is lined with the enamel. Enamel, as our teeth are also coated with the enamel to protection. So this enamel is used to protect the vessel from the corrosion. As we know, corrosion is the slow eating of the metal. Slow eating of the metal is called as the corrosion by the presence of the water and the oxygen. So we will protect our system by coat it with the enamel or any kind of a paint. So here you can see bomb calorimeter. In this bomb calorimeter, platinum crucible is present. In that platinum crucible, we place a sample. For that sample, we are going to use the do the combustion reaction. Here you can see the ignition point is also present. That is connected with the outside current. There are 2 points, positive and a negative, that are connected to the outside current. To provide this reaction ignition, we need to ignite the reaction. After that, in a combustion reaction, we just need to start the reaction. When the reaction is start, then we no need to provide the reaction, then the reaction is spontaneous. So for the ignition, we have connected this bomb. This is a bomb calorimeter that is placed in this vessel. This vessel contains water. Here is the water. So this vessel contains water. When the reaction takes place, before the reaction, we check the temperature of the water. When the reaction started, after every 30 seconds, we are going to check the temperature. So after every 30 seconds, we are checking the temperature. For example, temperature ends at, for example, ends at 150 degrees Celsius. So if the reaction stops at 150 degrees Celsius, then there is no change in the reaction, which shows that it is a final temperature. It is the final heat that is evolved from the system. The reaction is stopped because the temperature is constant. So by that initial and the final temperature, we are going to check the enthalpy of the combustion reaction. If we are using fuel, we are using any kind of fuel, any kind of hydrocarbons to check the combustion reaction, to check their enthalpy, we place that material in this bomb, steel bomb, which contains platinum crucible. In that platinum crucible, we are going to place our sample. Here you can see stirrer is also attached to maintain to evenly distribute the heat in the water. So this is all about the bomb calorimeter. This bomb calorimeter is also insulated, because if we are not going to insulate it, then heat will be moved towards the surrounding, and if heat is wasted in the surrounding, then we are not able to perfectly calculate the enthalpy change of the system. For the bomb calorimeter, the formula is used is Q is equals to heat capacity multiplied by delta T. Heat capacity is basically the increase of 1 Kelvin temperature of a substance. Here is not necessary the compound of 1 kilogram. In a specific heat capacity, we need 1 kilogram of a substance, but in a heat capacity, we just need to increase the temperature 1 Kelvin. So heat capacity is basically equals to the heat of the system divided by the change in temperature. We have rearranged the formula of heat capacity. Basically, this is the main formula of the heat capacity. Heat capacity is equals to the heat of the system divided by the change in temperature. So we have basically rearranged this formula to check out the heat of the system. So if we multiply the change in temperature with the heat capacity, then we will able to calculate the heat of the system, that how much heat the system evolved. This is all about enthalpy, measurement of enthalpy by glass calorimeter and bomb calorimeter. Tomorrow we will discuss about the examples or the problems related to these two topics.